there are like groups of types of chemistry problems. There's classic types of chemistry problems, and this is another classic. One classic that we recently did was the moles to mass and mass to moles problem for compounds and for elements before that. Or we're now working on compounds. We've worked on elements before. See what you think. Okay, so these aren't too bad, so I don't want to make them harder than they are. But there's a spin-off of this sort of problem. Percent elemental composition problem is basically you're given the formula of a compound. It could be a molecular compound or an ionic compound, and you have to, for each element in that compound, break it down how much weight is contributed by that element. Okay, it's not too bad. So there's a couple of different ways to work these, and in a minute, I'm going to give the baton to you guys, and you guys are going to work them. We're going to do this together. That's the extra credit point. So I'm actually going to pass around the iPad in this little stylus, and we're going to fill this in together. I know. This is to keep everybody awake. So bottom line, if acetone has this formula, 3 carbons, 6 hydrogens, and 1 oxygen, we need to come up with the weight percent brought by each element. Okay? So we need to kind of organize ourselves. So I'm going to turn this into a, so I can write on here. So you can write on here. And so we're going to start here and go over, and then kind of a logical sort of way. And there will be some times when somebody has to write the answer there. So I hope you have your calculators handy. You can use my calculator if you want to. So the acetone has the formula down here, so I'm going to kind of talk us along this. I'm going to start with Alexis, kind of pick on you. So up here, if you could, where it says first calculate the molar mass of the compound, just kind of get us started. Like how would you, using the periodic table, come up with the mass brought by carbon, hydrogen, and oxygen? And we're going to have you get your calculator out and write down the number.
So, okay. So just like the first step of the problem to do in the homework?
Yeah, just
like
the first step of the
3
problem.
times, yeah,
Yep,
okay.
yep. 3 times exactly.
This is really hard to write with.
You're doing good. Here, and we can make a little wrist guard down here if we pull this up. Oops. There.
Okay.
Remember, 10 points, people, 10 points. So calculate the molar mass of the entire compound.
Okay.
Okay, now we'll pass it over here. And it's insured, so, you know. Okay. And then ready for your magic underneath there. And what would those units be?
AMU.
Oh, wait, so it's molar mass, it's not AMU, so it would
Grams.
be grams per mole, and you can kind of write it right here. Perfect. Awesome. Okay, so in one of your homeworks that you did that was due today, I kind of gave you the hint. If you assume you have 1 mole of compound, that's a basis, and we're going to do that other times in actually this type of problem. So assuming we have 1 mole of the compound, can you help me out right here, actually for carbon, hydrogen, oxygen? If you have 1 mole of this compound, which correctly is 58.08 grams per mole, how much of that 58.08 grams is carbon? Flip around. Flip around. There it goes.
You want each one of them or just carbon?
If you're on a roll, you can do them all. Very good. He took 3 times 12.01. Any questions about that? I'm liking that. And last but not least, you go ahead and, I like it, can you go ahead and give me some more decimals here? 16.
One.
Perfect. Okay, so this is the mass per 1 mole. So can you say can you see where in 1 mole we simply have that grams, those grams, and those grams? Cool. I'm liking it. Thank you. So far, so good. I need a little tether thing so it doesn't fly off. Okay, so the next slide goes like, oops, this one.
Isn't it the same?
Yeah, it is the same one. Please. All right. So again, on the 1 mole basis, weight percents are always mass of the component divided by the total mass. So looking at the sheet we just did, for carbon, can you see what the mass of carbon in 1 mole is and what the total mass of a mole is? So it's the mass of carbon divided by the total mass of the compound. And it is hard to write on, but you guys are doing great. Okay.
Do I do it?
Oh, I
Okay.
set you up.
Yeah.
Sorry, not on purpose. It wasn't in writing mode.
So,
Yep.
that's a G, but yeah.
Mm-hmm.
V.
And I guess what we'll do is alternate. If you could go ahead and calculate that out and write down the equal sign, that'd be great.
For me?
Oh, wait, no, he's got it. We'll do,
Yeah.
you can do H. Yeah, I agree. And the rules of rounding work on these too, so. 4 sig figs.
I'm gonna
Perfect.
do that. There.
Yay.
And on them for each. So,
I think if you put units of grams and grams, that would be great.
grams and grams?
Thank you.
Is that right?
We'll have to come up with another problem. Thank you. Very good. So now if we added those all together, what should they be equal to the percentages? 100%, yeah. Perfect. Okay, so it's just a weight percent problem. Not too bad. Yes?
If you found 2 to the 3, could you just subtract the 2% from 100?
You could. You could, as long as you show your work. If you found 2 of the 3, just by difference, you could get the third one. Definitely. Yep. Okay, so I have a screenshot of these, and not so surprising then, these are what you think they are. Okay, so these look like this. No, they don't. That's later. They must look like this, hopefully. 23, 24. So basically, for the first one, you're going to have a weight percent of carbon, hydrogen, nitrogen, and oxygen. Not too bad, right? For the next one, you're going to have a weight percent of copper, carbon, hydrogen, oxygen. But I guess we'll just kind of make sure we're on the same page. So how many, in the second compound, how many copper atoms are there in one repeating unit? There's just one. Very good. How many carbon atoms?
36.
There are 36. And then hydrogen atoms?
66.
66. Yep. Oxygen?
4.
4. Yeah. So just don't forget that. Let's see. All right. So those will be due on Wednesday. Well, I think I mentioned this before. We're used to a formula of a compound telling you what atoms there are in that repeating unit. Well, there's kind of two broad types of formulas. There are empirical formulas and molecular formulas. And when I think of empirical formulas, I think of kind of sometimes a reduced formula. And sometimes no reduction can be applied, okay? But a molecular formula, I generally say, gives the most information. And I hope you'll see what I mean. The most info. Okay? So what they both do is basically tell you which elements are present in that compound, and as a minimum, what the empirical formula will do, the reduced formula will do, will give you the relative numbers of each element. So for instance, the real formula for butane, it's got 4 carbons and 10 hydrogens. That's it. It's a molecular compound. There's no metals there. So it's molecular instead of ionic. You can reduce it by dividing 4 and 10 both by 2 and get 2 and 5 respectively. Okay? So there on the right is its empirical formula.
So the empirical formula is always the lowest amount you can reduce it to?
Right. Exactly. And sometimes you can't reduce it, like water. You have subscripts of 2 and 1, and you can't divide it by an integer and get a different set of integers. Okay, so the molecular and empirical formula for water is both H2O. Okay, hydrogen peroxide, H2O2. Okay, I call the second one like Santa Claus. This is ho, 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 ho. Okay. What they both tell you is there's hydrogen, oxygen in there, and even if you look at the more complicated, the fuller molecular formula, for every 1 hydrogen, you have 1 oxygen, H2O2, and that's what this is saying. Hydrazine we looked at before, N2H4, of course you can divide both of these by 2 and get 1 and 2, respectively. Acetylene, and these next two are my favorite. Okay, acetylene and benzene, 2 different compounds with different properties. Okay, but they both distill down to the same relative number of carbons and hydrogens, 1 to 1. Okay, so they have the same empirical formula but different molecular formulas. So we talked about compounds as either being a molecular compound in which there's no metals, or ionic compound in which there is a metal in the formula. In general, ionic compounds are almost always written in the reduced form. And that kind of goes to, if you think of, I talked about those crystalline lattice structures, where you're like, I don't know which ionic compounds always have a cation and an anion. I just don't know which goes to which, so you just circle a pair. Okay, so they're usually reduced. That's the way I think of it. Okay, so what you guys did was you came up with a weight percent for acetone, weight percent of carbon, hydrogen, oxygen in acetone. Okay, but honestly, the formula for acetone, that, what was it, C3H6O? Can't remember. Yeah, that was it. That formula for acetone also gave the relative amount. They both give relative amounts. It's simply, and we're going to make use of this, it's simply that the weight percent gives it on a mass basis, and that empirical formula, for instance, for acetone, C3H6O, it gives relative amounts not by weight, but by moles, relative moles of carbon, hydrogen, and oxygen, 3, 6, and 1. Okay, so they both give relative amounts. All right, so another type of problem. First off, do you see where this problem up here you were given the empirical formula for acetone and you calculated the percent weight, okay? But you can also, if you're given the percent weight, and we're going to do this problem, we can backtrack and come up with the relative number of moles of each element. So basically what we can do, if you're given weight percent for each element in the compound, you can backtrack and come up with, for instance, I kind of call it this way. If it was acetone that had carbon, hydrogen, and oxygen in it, the subscripts of X, Y, and Z, that's supposed to be Y there. You can backtrack from weight percent to come up with what's the formula. But notice it's just the basic formula. It's the empirical formula. Okay. There is a way to get to the molecular formula, and we're going to cover that. So, we're going to pick up where we left off. Okay. So it goes like this. This is we don't know what the formula of this is a hydrocarbon, maybe oxygenated hydrocarbon. I don't know. It's hydrocarbon with oxygen in it. We have these weight percents, okay, and we're supposed to come up with, just to kind of reiterate what our goal here is, I usually think of it this way. Somebody says we have carbon, hydrogen, and oxygen in there. There's the weight percent. We want to know the relative numbers of moles, the empirical formula. So right off the bat in the corner of this next slide, what I was going to do, and I'm not going to right now, okay, is, go back. I wanted to emphasize, and I was going to have you guys knock this out, set our basis. It's not 1 mole now, but it's 100 grams. The reason we choose 100 grams is our basis. And honestly, I need to fix this screen. You need to show this, i.e., you need to communicate. Not just for yourself, but for somebody reading the rest of your problem. So obviously, if you have the weight percents, okay, if you go ahead and say, I'll start with 100 grams of the mixture, then you just turn those weight percents into grams. Does that make sense? Okay. Now, psych. I think we're still in writing mode. So if you could, that first one, how can we use that mass to get to moles per liter? And I'll have you go ahead and, you've got a calculator. And so you guys can be looking forward. We're going to do hydrogen and oxygen. And everybody can do that.
Wouldn't it just be,
Probably.
would I have to use that?
Yep. 12.01. And I would make this my first term though.
Right.
Right. You're right. It just. Cool. Perfect.
Shoot, how do you go back?
And if you want to go back, this little thing will let you go back.
Oh, sweet.
I know. There's like a little hurricane at the top there. Like you can go backwards if you want to. And one thing about it while Andrew's writing that is if you've labeled your problem, kind of like you see it labeled up there, then you don't have to be explicit about 53.3 grams of carbon over 1 times 12 moles of carbon for 12.01 grams of carbon. Times 1 mole of carbon over 12.01 grams of carbon. If you label it as you go, it's just kind of easier. So 3 sig figs. Dum, dum, dum.
That'll break this.
Yeah, pushing hard enough.
Okay. So, empirical formula for based upon those weight percents and going with a 100-gram basis, we kind of scaled them up to integers and came up with this empirical formula. No, there's no one there. So here's my thing. If you get relative number of moles, be careful of rounding, especially if you recognize in the decimal portion. If you're running a third in the decimal, so 0.33 or 0.67, or if you're running any version of a quarter, 0.25, 0.50, 0.75, do not round them. And I'll kind of show you what I mean. Okay? So for instance, if you came up with relative moles of 1.5 moles to every 1 mole, in order to get that 1.5 to a whole number, can you see we can multiply that by 2 and the number 1 by 2. So kind of scaling that up, that's really a 3 to 2, okay, relationship. I said watch out for thirdsies. So we can multiply the numerator and the denominator by 3. And then we can actually, then 1 1/3 becomes 4, and 1 becomes 3. Okay, I said to watch out for quarters. So if you run into a quarter, multiply it by 4. If you run into a half, multiply it by 2. A thirds, multiply it by 3. So of course, 1.25 times 4 gives us 5. Okay, so we have a 5 to 4 relationship. And then this is 2/3, isn't it? 0.67. So if we multiply this by 3 and this by 3, then we get a whole number, 8 to 3. Okay, so kind of keep your eye out for that. And I'm going to show you, again, I like the table kind of approach, because if I get a quarter, a third, or a half, I will make one more column, and I'll say multiply by 2. Make one more column, multiply by 3, whatever correction I need to do. So we're going to do another one, and we're back over here. So what is the compound's empirical formula? So this is what I meant to do at the top there. If you just say, if we have 100 grams of the compound, based upon those weight percents, what is the mass of carbon and hydrogen? Oh, wait a minute, I forgot to click the pencil thing. Thank you. Perfect. That says as much, that you go ahead and you divide the big number by the small number. There's only 2 numbers here. And when you divide it out, you notice that you have 2.5 moles of hydrogen for every 1 mole of carbon. And again, that should be a flag. You got to do something with that 2.5 other than rounding up or down. And to fix it, you multiply both numerator and denominator by 2. Okay. So, and this is kind of a repeat slide. Yeah. Okay. So this is that last sort of problem where it is possible to go from weight percent through empirical formula to get molecular formula, okay, if you know the molar mass of the compound. And I'll show you how that works. So the big thing here is you also need to know the molar mass of the compound. Okay. And we're going to pick on one we already did, which is kind of nice. Okay, so way back earlier we did, given these weight percents, I guess we didn't know the identity of the compound. Based upon its weight percent, we know that there are 2 moles of carbon, 5 moles of hydrogen, 1 mole of oxygen in that empirical, the reduced formula, empirical formula which may or may not be the molecular formula for that compound. Somebody goes ahead and gives us more information. They say if the molar mass of the compound is 90.1 grams per mole. Basically, and I'll kind of give it away on this slide. Basically, if you're going to find the mass of that unit, the basic unit, and see how many of those you need to scale up to get the overall mass. Okay, so that's basically it. So an empirical formula, that's something that's been reduced and you want to scale back up, you can think of the empirical formula in parentheses, and then outside that is a little x, and then x is an integer. So you can scale it up 1, which would mean that the molecular formula and the empirical formula was the same. You can scale it up with a 2, okay, in which, in this case, if you needed 2, those would be what? C4H10O2? You know, any sort of scaling up of that repeating unit. Okay, so what we need to do is use that molecular, the formula, or what we need to do is use the molar mass molecular of the molecule, and to see, like I said, how many of the smaller repeating units are within there. So thinking of it another way, the overall molar mass of the compound is equal to x times kind of this, let's see what I call this, the repeating unit. So for this particular compound, we found this is the repeating unit, and we're going to scale it up to some to make the overall molar mass. So actually, if you want to go ahead and think of rearranging, solving for x, which is the number of times you repeat it, all we got to do is take the little unit mass, okay, take the little unit mass that's in the bottom, okay, and divide the molar mass into that. It's easier to show you than to. So using the periodic table, we look up the number for carbon, hydrogen, oxygen. So the repeating unit of C2H5O has a molar mass of 45.09 grams per mole. You see where we're going with this? If you take that times 2, you get your 90, right? And that's it. That's the deal. So the scale-up factor is basically taking that empirical formula and multiplying each of the subscripts by 2. So even though that is the empirical formula, C2H5O, the molecular formula is C4H10O2. So again, what we did was to go from the empirical formula, the basic formula, up to the molecular formula given the molecular weight. Not too bad.
So our answer has to be the C4, or does either one of them work?
So the answer as the molecular formula is the scaled up one. Yeah, it's the C4H10O2. Yep.
And you can't write it with the parentheses, it has to be.
Yeah, you would want to write it with the parentheses. You would want to multiply this 2 in. Yeah. So this is the molecular formula. So you guys write better than I do. And this was its empirical formula that we got from the weight percent. So I have screenshots for the problems with some hints. We'll see what you guys think. So these will also be due on Wednesday. I'm not on campus on Tuesdays, but I do answer my phone. So I'll just go ahead and kind of show you the whole thing here. 23 and 24 are both very similar. You're given the formula for the compound, and they're kind of fun. Just go ahead and write them out. Make sure you organize yourself. But for the first compound, you have carbon, hydrogen, nitrogen, oxygen. What's the weight percent brought by each element? Okay, it's like your first problem that you did. The next problems go like, so those two are very similar. There's a song that goes, enjoy yourself. You should just enjoy yourself. Well, maybe I'm not gonna. Oh, I guess, okay, wait a minute. The next one, oh, darn it. Okay, the next one, I think I got this down. 31 and 32 kind of go together. This was where you're given your weight percents. And remember at the top there, I say consider 100 grams of the compound. That's what I would do. Communicate that. You don't have to set it up in rows like this, but you can. And so based upon those weight percents, notice since like Matthew was saying, notice in this case you're given a compound you know has carbon, hydrogen, and oxygen. You're not given the weight percent of oxygen, but you can get to it by difference. Okay? And the last one, maybe it's not the last one, but the next two are kind of similar, 35 and the next one. Remember you have the answer in the back of the book to this one. This is like we just did. Okay, where you're given the weight of the overall compound, 178. Remember, U's are AMUs, same thing. Okay, and so first you're going to have to use the weight percent to get to the empirical formula, and then you're going to take how much that repeating unit is, and you're going to divide 178 by that to find out how many repeating units is. And then the last one is similar. So.
Are we still gonna have our study group?
Yeah.
Wednesday morning at 9, right?
No, it's
You guys might have another one going. Mine's on Wednesdays mine's Wednesdays at 3. But you can have a, you know, because it didn't work for everybody. Okay? Very good.